Have you ever wondered how rotation works in BFDI? Is it similar to rotation in the real world, or is it different? In this video, I will apply concepts I developed in my previous videos to understand rotational motion in BFDI. To understand rotational motion in BFDI, it's important to understand rotational motion in the real world, so I will explain it in the next part of the video. But if you are already familiar with these concepts, you can skip to this timestamp. For a body to rotate in a circle with a radius of 1 unit and a constant angular speed of 1 radian per unit of time, its x position is cosine of t, and its y position is sine of t, where t is time. If the body has rotated around the circle with larger radius, the x and y positions are multiplied by r, and to make the body rotate at a different rate, t is changed for omega t. But what is the velocity of the body? To find it, we can find the derivative of the x and y positions. The derivative of x position is minus omega r sine of omega t, and the derivative of y position is omega r cosine of omega t. If we calculate the magnitude of velocity, we find its omega r, so the x and y components of velocity can be written as minus v sine of omega t and v cosine of omega t, where v is the magnitude of velocity. Since we know the speed of the body, we can integrate it with respect to time to find that the distance traveled as a function of time is vt, which is equal to omega rt. For the body to stay in the circle, the velocity has to be tangent to the circle at the point that the body is at. This can be verified by taking the difference in two position vectors, which are separated by a small angle. For this to be the case, the velocity vector needs to change with time to be tangent to the circle at different points. This means that there is an acceleration, called the centripetal acceleration, which is the derivative of velocity with respect to time. The derivative of the x component of velocity is minus v omega cosine of omega t, and the y component is minus v omega sine of omega t. So the acceleration has a constant magnitude of v omega, which can be rewritten as v squared over r or omega squared times r. So we can do a similar thing to velocity and write the components as minus a cosine of omega t and minus a sine of omega t. For the velocity to always be tangent to the circle, the acceleration has to point towards the circle. This again can be verified by taking the difference of two velocity vectors that are separated by a small amount of time. But what is the physical meaning of omega? The x and y components of position are r cosine of omega t and r sine of omega t, so omega t is the angle of the body. This means that omega is a derivative with respect to time of the angle. Because of this, omega is called angular velocity. We can also relate angular velocity with the linear velocity of the body. First, we need to know how to convert between distance and angle. If the body traveled a distance equal to the radius of the circle, the angle changed by 1 radian, since that is the definition of a radian. So the difference in angle is the distance traveled divided by the radius of the circle. By taking the derivative of both sides, we find that the angular velocity is equal to the linear velocity over r. There is still one topic I haven't covered. How do you change the angular velocity of the body? The answer is with torque. Torque is equal to force times radius times the sine of the angle between the force and the center of rotation. This is equal to angular acceleration, which is the derivative of angular velocity, times the moment of inertia, which is mass times distance to the center of rotation squared for point masses. For bodies made out of multiple masses, the moment of inertia is the sum of all masses times their distance to the center of rotation squared. The way that these equations are derived will be shown later because it doesn't depend on the order of the force. Now that we know rotational motion in the real world, we can generalize it for BFDI physics. The main difference between physics in BFDI and real life is that in real life, force is mass times acceleration. But in the theory I have been developing for BFDI, force is not just mass times acceleration. There are multiple different types of forces, called forces of order n, which are mass times the motion of order n. And the motion of order n is the nth derivative of position with respect to time. So the motion of order 0 is position, order 1 is velocity, order 2 is acceleration, etc. The main thing that we need to know is how forces of different orders affect the position of a rotating body. So a good point to start generalizing rotational motion may be to change the equations for the x and y positions of the point, such that instead of omega being the angular velocity, it's some derivative of different order of the angle with respect to time. To do this, we can replace the t in the equation with t to the n. But let's also divide this by n factorial, because I think it makes later formulas simpler. By taking the derivative of x and y position, we find that these are the x and y velocities, while the magnitude of the velocity is this, and the distance traveled by the body is r times omega times time to the n over n factorial. The velocity is still tangent to the circle, but now its magnitude changes. To find the acceleration and the other motions, we can still take derivatives of the motion of order n minus 1, but the expressions get quite complicated from here, so it's hard to understand rotational motion based on them. There are other ways that we can find quantities that are motions of order n. Since we know that this is the distance traveled as a function of time, we can derive it n times to find that the motion of order n is r times omega. Thus, it makes sense to call this omega angular motion of order n, written as omega subscript n, where n is the power that t is raised to in the sine and cosine functions, to match the notation used for motions of order n. With this notation, we can write motion of order n equals r times angular motion of order n. One thing to note is that this motion of order n is not the actual magnitude for any motion of the body. Consider a body rotating with a constant angular motion of order 1. Since its angular motion of order 2 is 0, by motion of order n equals r times angular motion of order n, the motion of order 2, or acceleration, is also 0. But we know that the body has a centripetal acceleration equal to v squared over r, which is not 0. The reason as to why these results are different is because in this case, the acceleration doesn't change the magnitude of the velocity, but in the derivation of motion of order n equals r times angular motion of order n, we took the magnitude of the velocity, integrated it, and then derived it n times. So this motion in the formula doesn't describe the actual linear motion of the body. It's the nth derivative of the distance traveled with respect to time. The only case where this motion is equal to a motion of the body is when the order of the motion is 1, since it is the derivative of the distance traveled. The angular motion of order n is also equal to the nth derivative of the angle with respect to time, since this is the angle, and if we take the derivative of both sides n times with respect to time, we get that the angular motion of order n is the nth derivative of the angle. We could also consider a more general case of rotational motion, where there are many different orders of angular motion, and the angle as a function of time is given by this polynomial. Then, these are the x and y positions, this is the distance traveled, and we can find the motion of order n by deriving the motion of order 0 n times with respect to time. Now we need to generalize torque, and for that, we need to understand the derivation for torque. The derivation I used is based on the one at the end of another comment on the physical origin of torque and of the rotational second law. The derivation assumes the strong form of Newton's third law, which says that when two bodies interact, the forces have the same magnitude, opposite directions, and are parallel to the line joining the two bodies. This is true for the real world, but might not be true for BFDI. However, understanding the case where this law is true might make it easier to understand the case where it is false. Let's consider this setup where two masses and the pivot are all connected with rigid rods, and the force F is applied on mass 1. The forces T1 and T2 just keep the body at a constant distance from the pivot, so they counteract the radial components of any forces, and we can just consider the tangential ones. So we get that the net force on M1 is F sine of theta minus T1 2 times sine of theta 1, and the net force on M2 is T2 1 times sine of theta 2. Since the rods connecting the points form a triangle, both masses have to rotate together, so they have the same angular motion. Therefore, we can say that f sine of theta minus t12 sine of theta 1 equals m1 r1 times the angular motion, and that t21 sine of theta 2 equals m2 r2 times the angular motion. According to the law of sines, r2 over r1 equals sine of theta 1 over sine of theta 2. And since we are assuming the strong form of Newton's third law, T12 equals T21. From the law of sines equation, we get sine of theta 2 equals sine of theta 1 r1 over r2. So m2 r2 squared times the angular motion over r1 equals T12 sine of theta 1. Then, by adding both sides of this equation to the equation for m1, we get m1 r1 plus m2 r2 squared over r1 times the angular motion equals f sine of theta. If we multiply both sides by r1, we get m1 r1 squared plus m2 r2 squared times the angular motion equals f times r1 times sine of theta. Then, if we define torque of order n, written as tau subscript n, to be Fr sine of theta, and the moment of inertia, written as I, to be m1 r1 squared plus m2 r2 squared, we get torque of order n equals the moment of inertia times the angular motion of order n. If we take the derivative of torque using either expression, we find that torque of order n is the derivative of torque of order n minus 1. But what if we have more than two masses, and all masses have an external force applied on them? What is the angular motion in this case? We have these equations, and we can find that the angular motion times the moment of inertia equals the sum of the torque of each force. This is a derivation. We can also apply torque to situations where the strong form of Newton's third law is not true. Let's consider a similar setup to the previous one with multiple masses. All masses have forces applied on them due to the interactions with other masses. Here, we can just calculate the torque of each force and add them to get the net torque, like in the other cases. However, all masses need to have the same angular motion, which puts a constraint on the forces applied on the masses, which can be rewritten as an equation of forces or torques. For a group of particles to behave like a rigid body, this equality has to always hold for any two particles. Looking back at all the results in this video, the changes made to rotational motion to account for different orders are similar to the ones made to linear motion. The angle as a function of time is a polynomial where the term of degree n is the angular motion of order n divided by n factorial, just like with linear motion. The derivative of torque of order n is torque of order n minus 1, like forces, and torques of different orders behave in the same way as torque of order 2 in the real world. These results are what I expected based on intuition, but it's good to prove things rigorously. This is all I have for this video. Goodbye.